Okay, in the last class we have been discussing about the resistance estimation using a Holtrop-Menon method, and Holtrop-Menon method is normally used for conventional shapes which can be either a single screw or a tin screw. Now we move on to the next method which is available for the estimation of resistance of small crafts, mainly the trawlers and tugs. So this is put forward by Van Woodmerson based on the experimental studies which he carried out, and see the limitations of this application of this method is length of on water line is between 8 and 80 meters, then volume displacement 5 to 3000 meter cube, L by B length to breadth ratio 3 to 6.2, breadth to draft ratio 1.9 to 4, and the prismatic coefficient 0.7 to 0.5 to 0.73, midship area coefficient 0.7 to 0.97, LCB 7% from aft of midship to 2.8% to forward of midship, half angle of entrance 10 degrees to 46 degrees, then V by L power 0.5, that is volume displacement length raised to 0.5 is coming to up to 1.7 and Froude number up to 0.5. So if the vessel which you consider fall within this range and the type of vessel also is the same as trawlers or tugs or small crafts, then naturally you can try this method for the estimation of resistance in the preliminary stages of the ship design. Here the what as we have discussed, the total resistance using the Froude hypothesis has been split into residuary resistance and frictional resistance. So frictional resistance usually taken from ITTC formula, and residuary resistance formula is presented here. So the residuary resistance with in relation to the weight of the ship, non-dimensionalized here, both forces, force quantities here. So which is represented by this expression. You can see that C1 into exponential minus m by 9 Fn square plus C2 into e power minus m by Fn square plus C3 into e power minus m by Fn square into sine of 1 by Fn square plus C4 into e power minus m by Fn square into cosine of 1 by Fn square. So this is the expression put forward by Van Woodmerson based on a regression analysis carried out on the experimental data obtained through the model test. So here it's all clear. Fn is a Froude number, it's a length Froude number used, Cp is a prismatic coefficient what is used here. M what appears here is now represented by using this formula, which where the prismatic coefficient is a parameter. The coefficients Ci, you can see that C1, C2, C3 and C4. So Ci, I varies from 1 to 4 is given by this expression over here. That is this expression which depends on LCB, depends on the prismatic coefficient, depends on LD, that is a displacement length by B, then you have the LD by B here, then what plane area coefficient, B by T ratio and also midship area coefficient. So it depends on the major geometric parameters of the vessel. So at this stage of the design you are expected to have all these things known. So then you can find out what is the Ci from the table appearing in the next slide, and these Ci values you can just put it here to find out Ci and M and Froude number everything. We get what is RR by W. So here LD is the displacement length given by this formula, LD is equal to LWL plus LBP, that is average of that, mean of that. LCB we already know that, which is appearing here, the LCB here it is LC, that is a longitudinal center of buoyancy with reference to the midship, you can see that. So B is a beam and T is a draft, and CWL it can be taken as IE, that is a half angle of entrance by LD by B. So once you get all these parameters and use the coefficients which has been already prescribed by Van Hout-Merson based on the analysis. So, you can see that for di, that is 1, 2 and 3 are the values of I. So, if you look back, you can see that here Ci 1000 into Ci. So, here 1 I is C1, that C1 goes here. So, if you want to find out C1, use this expression with I is equal to 1. For I is equal to 1, that means you have to need 1 D10, D11, D12 like that for C1. So, if it is for C2, then you need Z2 1000 C2 is equal to D20, D21, D22 like that. So, you get all the C values, and you can go to this expression and put the values and get the residuary resistance. So, that is what you get here. So, when is equal to, when you want to C1 you use these values, when you want C2 use these values, you want C3 these values and C4 these values. So, these are the coefficients, regression coefficients, and based on which you will be able to find out, knowing other parameters, this resistance, residuary resistance. So, once you have obtained the residuary resistance, then you follow the ITDC formula to find out the frictional resistance, and also use the form factor from which you will get the total resistance, and that total resistance then you have to add correlation elements and other air elements, air and wind elements and all that, from which you get the total resistance of the ship which you design, and from which you will be able to find out the power requirement and subsequently the power of the engine required for the ship. So, the next method what we look into is the Guldammer-Hauwald method. This is also a popular method, again used for conventional ships and generally used for both single and twin screw ships. So, here the specific resistance coefficient Cr has been expressed as a function of Froude number, which is obvious because it is related to Cr is related to Froude number. Then the residual resistance coefficient is plotted against Froude number in a group. We have already seen that if you know the chart, the series diagram normally put forward by Guldammer-Hauwald. We are not going to use a diagram here, we just explain based on the regression expression. So, these starts are, that is for each value of 1 by L by delta power 1/3 a set of data is available. So, the charts of Guldammer-Hauwald charts are meant for L by delta power 1/3 values of 0.4, 0.45, sorry 4, 4.5, 5, 5.5, it goes up to 8. So, these are the charts which are available based on the studies performed by Guldammer-Hauwald. So, the resistance curve diagrams corresponds to vessel with standard, all the tests have been done within a standardized form. So, the tests have been done for a standard position of LCB, location of buoyancy, then standard B by T, the shape is taken as normal section and cruise astern is taken as moderate, and it does not consider transom stern here, it considers cruise astern which is moderate shape and raked stem. So, these are the assumptions, or these are the values which are being used for the models, preparation of the models, and such models have been tested and the data have been obtained. So, whenever there is a deviation from these values, you have to apply correction to the values of the CR values which you get to use for a ship which is not deviating from these standard values used by Hauwald. So, the limit of application of this method, you can see it is L by delta power 1/3, 4 to 8, that is what I said, it starts from 4 then with a 0.5 increment, 4.5, 4.5. So, you have the charts available for these values. Then the prismatic coefficient varies from 0.5 to 0.55 to 0.85, Froude number 0.15 to 0.45, and V by square root of L, L taken in feet varies from 0.5 to V in knots and L in feet, it varies from 0.5 to 1.5. If the ship falls within this range, then, and it is a normal conventional vessel, you can use the Goldhammer-Howard method. So the raked stem, what I think you know that what is a rake stem, there is no bulbous bow considered here, it is a normal rake stem, straight stem, and the section shapes normally it is divided into normal section, then U section and V sections. So if you are deviating from the normal shape, or if you are using U section or V section, then you have to give a correction for the change in the section shape. So this is the expression coming from that, in place of chart it has been put in this form. So the empirical formula here is 10 cube Cr, because Cr is a small quantity, it is a coefficient, is a non-dimensional parameter, and hence it usually is very small. So it is, that is why it is presented often by 10 power 3 Cr. So that is equal to E plus G plus H plus K. So each terms are defined below. So once you have evaluate these terms, then you can find out the, okay, put it over here and get the total residuary resistance coefficient. So here the E term, if you look, it is given by these parameters A0 and Fn, A1, and then you have the M coming here, M and Fn. So you see that what are the coefficients, parameters here, A0 given by this expression, it is depending on M alone, and A1 also depending on M alone. So M is defined as L by delta power 1/3. So once you know L by this value, you can just substitute it here, and also N1 which appears here, you can see it is represented again in terms of M. So you have these values, all the values are known from here, and then substitute it here, you get E. Then G, the second term here, it is given by B1 into B2 by B3. So the terms of explained here, B1 depending on M, B2 depending on Cp prismatic coefficient, and B3 depending on the Froude number, and once you get all these parameters, you can find out what is G, and G will go here. Then you have H exponential as e power of these quantities here, Fn, Cp, M, all these quantities are known, H will be put here, then K value is depending on Froude number and prismatic coefficient. So these values again, so you get the standard, that is as per the Goldhammer-Howard standard, what is the 10 cube Cr, that is the residuary resistance coefficient of the vessel which you are considering for the design. So whenever there is a deviation, of course the B by T here assumed is 2.5, that is a standard B by T assumed by Goldhammer-Howard. If the vessel which you consider for design is deviating from this, you have to give a correction in 10 cube Cr for the B by T. So here you can see the B by T correction, 10 cube Cr is equal to 10 cube Cr standard, that is the one which you have seen before, plus 0.12 B by T minus 2.5. So which implies that if B by T is less than 2.5, then it can be negative. If it is more than 2.5, then you have to add, it is physically correct, when the beam of the ship increases, resistance increases, isn't it. So when B by T is more than 2.5, the resistance Cr will increase, or if the more slender, that is the B is reduced, resistance comes down, and so this quantity become negative. So which is taken care of in the correction in this. The similar corrections are also available for LCB when it deviates from the standard value, then also the form, if you are using not the normal form U or V, then there will be a correction for that. So considering this, then if you are having not a cruiser stern, you have a transom stern, there will be correction for that. So including all these corrections as a small correction which are not covered here, so you will get the corrected 10 cube Cr. So once you have achieved that corrected 10 cube Cr, then again you estimate the frictional resistance using the IDTC formula and get the form coefficient, the form factor, and using that you will find out the total resistance by putting the other model ship correlation elements and that is Ca, which you put 0.0004, then the air resistance and other things you put, then you get the, you can predict the resistance of the ship under design. The next method here is the Funk's method. So here you can see these are the basically this is for transom hull vessels we have carried out. It is a relatively new method 1995, and various parameters used in this are explained here, where it considers transom area as a transom ship which is considered, transom area with relation to the midship area may be considered, prismatic coefficient, the transom width, and the B/T ratio, half angle of entrance, midship area coefficient, wetter surface area. So all these are considered in the estimation. Okay, Funk method, it is represented, it puts the residual resistance coefficient Zr is equal to exponential of summation of this one, it is a product sign. So you have this is a quantity over here, and now you know that n I think is coming up to 69, n is a total number of 69 coefficients, we will see the coefficients later, n value. So I is equal to 1 to n and j is equal to 1 to 9. So what you have is the j here it is 1 to 9, so you get x1, x2 up to x9. See how this x1 are represented, x1 is equal to fluid number raised to d, so x2 is equal to given by cosine of lambda into fluid number raised to e exponential a by fn square, x3 given by this formula, this is the mass displacement of the ship, x4 it is this area of the transom, that is submerged area of the transom divided by area of midship section underwater, then x5 the prismatic coefficient square, x6 the breadth of the transom at the waterline, and b is the breadth of the ship. So once you know all these parameters, you can then this is x7 is B/T and x8 is the length into 90 minus IE, x9 is Cm, then lambda which appears here is given by this expression which depends on Cp, again mass displacement LWL. So these coefficients which appear here, you can see that D, E, A and also maybe other A1, A2 and all that, you can see these coefficients are given like this. These are the values for the these parameters, not the coefficients, these parameters. So finally what you need is, now you know what is x1, x2 up to 9, you have these values, and what you look for is b values, then you have the, you need the Cij. So we said that we look into what, how do you get b and Cij, and based on which you find out. So here this is b, you can see I is the total number of terms, we have seen 69. So this column will go up to 69, this column is up to 10, and maybe next slide further it goes to 69. So for particular I, what is the value of the excess? So the power of that is given here, that is you have seen that it is x power Cij. So what is the power given for the x corresponding x, that power value is given here. So once you get the b I particular row, you get all these quantities, you can see that sorry, this is the first this all zeros here. So if you go only you have b, all these are 0, so it becomes 0. Then you have here bi b1 is equal to minus 5.38179, and only x1 will have a power, other terms are not significant. So you get, it goes like that, the powers will be 1, and other powers means 0 means x raised to 0 1, x 2 x 3 raised to 0 again it is 1. So other terms are become 1 only, so only the x1 will have the power 1. Then so you just continue with that, you have the similar diagram for regression coefficients, it goes up to similar 20 now, 30 here, 40 here, 50 here, 60, it goes up to 69. So there is a total number of coefficients here. So all the coefficients are given here. The power keep changing, maybe 2 here, you can see that some powers are different. So it is a straightforward method. Now you know you will be able to find out the CR using Goldhammer-Harvard. Conventionally use a chart, the data presented in a chart form has been used. Here what it explains is based on the regression expression, and using the regression coefficients the whole chart is now converted into regression, because when you convert it into regression expression, computerization become easier, calculation become easier, to program the expression is easier than programming the chart values. So that is a reason here. So the limitation, what this is applicable for what all, what is the limitation of this Funk method? V by L cube, that is volume displacement by L cube, this is a range, V by T this is a range, prismatic coefficient you can see this is a range, Meship area coefficient this is a range, half angle of entrance this is a range, L by B length by breadth ratio this is it, and water plane area coefficient is this. So just look to your ship if it falls within this range, and then you can use the Funk's method. So all these methods basically are meant only for design purpose. The final thing, you have to perform a model test, then you have to estimate the resistance before finalizing the resistance and subsequent selection of the or determination of the engine power and selection of it. So the next method is Mercier-Savitzky method. Whenever you say this method, obviously referred to, it's a planing hull here for displacement hulls and also for planing crafts in the displacement mode. So this can be used for displacement hulls, usually smaller vessels, and also for planing crafts in displacement. Planing crafts planes only at a higher speed, so the initial speed at lower speed it operates as a displacement mode. So when the speed reaches a threshold point, then it starts planing, and then you consider it as a planing vessel and the resistance is determined separately. So here this method is applicable only for displacement ships and for planing crafts in the displacement mode, not in the planing mode. So general form of the equation is given by this, total resistance by weight of the ship is given by this one, A1 plus A2x plus A4u plus A5w A6 x is set. So it goes like that. So it goes up to A27, many a's are missing in between because this is the form it has been used, and this equation is based on development of the study carried out for a displacement weight of 100,000 pounds or equal to 445 kilonewtons. So here the x which appears here is explained as the volume displacement power 1/3 divided by L. So that is the x definition. Z which appears here is defined as volume displacement b power third, that is the breadth of the ship power third. Then u is equal to square root of 2 times the half angle of entrance, that is a u appearing here, it is defined like this. W which appear here is area of the transom divided by area of the midship, again below the water line. Then the Froude number is depending volume, so this is the definition of volume, the Froude number definition, V by square root of g into volume displacement raised to 1/3. So this is the Froude number used, it is not the length Froude number used here, it is the volume displacement based Froude number. So then you have the RT by W, the correction, if it is a correction deviation from this, it is equal to this value plus this is the correction applied here, Cf prime which is coming from ITDC formula minus Cf Eq that is coming from the Hughes formula, I think you remember that, plus the correlation elements. So all this put together and multiply half S by p power 2/3 into the volume Froude number square. So from this you will get the corrected total resistance to weight ratio. So once you get this, then you get the total resistance straight from here. It is not that you have split in this formula, the total resistance is handled, unlike the previous expressions where only the residual resistance was considered, whereas in this case you have considered residual resistance, also the CF value is also taken care of in this value. So the vector surface area is given by S by V raised to 2/3 is equal to 2.2 L by V power 1/3 B by T and B by T square, here you can see. So once from this expression, by knowing these parameters, you will be able to find out the vector surface area. The correlation allowance is normally taken as 0.0004, but an expression is given here based on length of waterline, and this is the expression if the TF by LW, TF is the draft at the forward perpendicular, the draft at the forward perpendicular by length of the waterline, if it is greater than 0.04 use this, if it is less than 0.04 use this expression, and for at 0.04 you can use any of us, both will come to the same expression. So this is the Mercier-Savitzky method. So here the coefficients what you need A1, A2 etc. up to A27, that is what you need here, A1, A2 etc. up to 27, these quantities are given here. You can see that this is a A1 values. So A1 values are given for particular fruit number, volume fruit number. If volume fruit number is equal to 1, displacement fruit number is equal to 1, you get use these values. If the displacement number is 1.1, use these values. If the displacement fruit number is in between, you do both and then take interpolation of that for that value. So this is given for a range of fruit number 1 to 2 at an increment of 0.1. So the values are, you have to take the appropriate values for A1 to A27 and use the previous equation, then you get the total resistance. So these are the different, there are different other methods, maybe some of the resistance calculation methods for advanced vehicle, high speed vehicles and maybe catamaran, so we will be discussing later. So these are generally for this all meant for mainly displacement type of vessels, what you have seen, the methods what we discussed, Holtrop-Menon method, then Funk's method, Guldama-Howald method, all these are meant for displacement type vessels, even including the Mercier-Savitzky method. So it can be applied to planing vessels, but only for the cases when it is in the displacement mode. So these are the conventional methods or the data available to you based on experiments carried out by various research group, and this information is very much useful in the design stage of a ship. So when you design, you have to have an idea about the engine power requirement. So you have to know how much the power required for the vessel. So the power requirement is now depending on the resistance of that. So once you get the resistance at the service speed, then resistance into the service speed, that gives the effective power, and then you consider the transmission losses due to shaft, bearing, gear and all that, then you will come to know what is the power required at the engine side. Now you consider engine is not operated at 100% power always. So the maximum continuous rating is, usually the continuous rating of the engine is about 85 to 90% of the maximum power. So then you will know with the non-derating what is the brake power of the engine. Once you arrive at that brake power, then you go through the engine catalog, from which you will find out, you can choose an engine. Again different other parameters come into picture, what is the fuel efficiency, what is the size, what is the weight, what is the reliability regarding maintenance, and so cost of maintenance, availability of service, after sales service. So many factors you consider, then you select the engine. So once you select the engine, you know what is the weight which will go also as an input into the design, because when you do the weight estimation, the initial stages of the design, you might have assumed a weight for the engine, the engine plane mass we might have assumed. So here you are obtaining a correct mass which you substitute and proceed with the design further. So that is where these methods are useful. So a typical example of these methods have been applied to a LPG cylinder carrier. We just see that how does it compare. So these are the vessel parameters. We have considered numerical example. Vessel parameters here. This is a 37.59 meter LBP. This is the waterline length, breadth 9.5, depth 3.5 meter, and draft 2.5 meter, and this is other informations about the vessel. So then you have all these parameters coming here. Then yeah, you can just go through this, what are different area given and speed given, and so finally the transom area is given. So all these parameters are there available. So based on which you use all these methods to find out the resistance, that is you use the Holtrop, this is total resistance, this is residuary resistance, it is all in newtons. Wood-Mason has given that is under predicting very high, and here you can say Goldhammer and Fang, they are coming closer. So this method is off, maybe the vessel is not falling in the range of the Wood-Mason, because that is mainly meant for trawlers and tugs. Here the vessel is a barge. So the resistance calculating for various speeds using the different methods are given here, starting at a speed of 2 meter, it goes up to 12 meter. So you can see this is a variation over that, and later just plot it to find out the take us a feel of the variation in the resistance prediction. So here you already know what is the method adopted in the ITTC 1978 approach to predict the vessel resistance, where the total resistance of the model is represented by the residual resistance of the model plus the form factor into the flat plate formula expression used by ITTC 1957 for the frictional resistance. So conventional thing, you know that the CRM is equal to CTM minus 1 plus K into CFM. So that is the residual resistance coefficient of the model, and from which it is same as the CRS because it is satisfying the float number. CFM you have is coming from the ITTC formula. So CTS, total resistance, is equal to CRS plus 1 plus K into CFS. So you can see the CFS coming from here, this formula, and then the CTS you have put CRS is equal to CRM. So you get the total resistance coefficient for the ship. To that you add the correlation elements and wind or air factors and all that. So this is a geometry of the model, and this is a geometry. So the experiments also have been done using this ship and in the towing tank in IIT Madras. So the experimental results also available. We have also performed CFD analysis for the same vessel, and all the results are compared, and you can see here first comparing with the experimental results with the different methods. You can see the experimental method is given by this line shows the experimental method, and Wood-Mason is under predicting a lot. Then Goldhammer is coming, this is a line, Goldhammer line, this is the Holtrop Menon method, and this is a Fang's method. So this is a survey speed, you can see there is a variation, and some method you can see the experiment is getting closer to Goldhammer method at the survey speed, you can see it is very close. So that is a prediction, sort of prediction we have got from the different analysis using the regression expressions and also using the experiment. So later, as I said before, a CFD analysis was carried out using that. It is a wireframe model of the vessel, and the computation domain, it is that is this is the vessel here, and we have identified a domain for the computation, and it is taken as a boat length upstream is 3 times the length, one boat length upstream and this side, and 3 times the length this side, this is a downstream, and 2 boat lengths below, that is to get a deep water condition, and 1 above to include the air part, then 1 boat length in the transverse direction. So usually you mold it only half of it because it is episymmetric. So the boundary conditions use that inlet velocity inlet, volume fraction and component. So here this is the inlet boundary, and this is the outlet boundary. Pressure outlet volume fraction method is used. Then the wall, the shear stress with the slip is used, and body you have used a no slip condition. So mesh details are given here, and physical models selected, K epsilon model used, then RANS used, turbulent model, it is that is what is the K epsilon, volume of fluid V, sorry, that is the method used for that. Then you have these are the methods, and this is a closer view of the body with in the domain. CFD analyzed for this vessel, for this velocity, this is a model size has been generated in the CFD analysis. So this is a model speed and corresponding float number, and these are the model resistance obtained in newtons. So now the total resistance compared with all this CFD, and you can see that Holtrop method, that is for the model case, Woodmason, Goldhammer, Fung, experiment and CFD, and this is I think this is the service speed, and where you get the values coming reasonably close. You can see here this method except this Woodmason method which is totally off. So this is the plot of that for different methods. So subsequent to this another vessel was also considered for the CFD analysis for 1000 ton fuel barge. These are the particulars of that: 68 meters, 66 nearly 67 meters length at waterline. So these are the main particulars of the vessel, and these are the hydrostatic parameters at this design draft of 3.6 meters. So the volume displacement, center of buoyancy, position, wetter surface, everything is obtained for that vessel, and the same has been used for further analysis. This is a model 3D model of the vessel. You can see these different views. This is a top view, this is a profile view, this is isometric view, and this is a front view. Only again only half the model is considered because of symmetry. You can see here it's a symmetry plane here, and then it's a domain is analyzed fixed based on the standard dimensions. It's a closer view of the meshing. You can see the mesh around that, and this is a total resistance which has been obtained based on the CFD studies. So you can see this has been checked with later with the Goldhammer-Howald method, which is getting very closer to that within a deviation of 5 to 10%. So this is a speed resistance in newtons. You can see for various ship speeds for the prototype is plotted. Here the modeling is done for the prototype, not for the model size. This is all for the model prototype dimensions, and finally you get the resistance into velocity. You get the effective power. This is the effective power obtained from the computation. And here you can see that wave elevation, free surface for vessel speed of you can see this is the survey speed is 12 knots in this case. You can see the wave elevation here. You can see the wave is coming to, if you look to a scale, is coming to 1.7. You can see it's a draft of 3.6 meter. The bow wave is going up to 1.7 meters above the water level, and you can see here the wave size is there, and here is a dip, there is a trough forming here, you can see the scale is low, it is a trough formed here. So generally this shows that this region is having a high wave which increases the resistance of the ship. So if you redesign the form, reduce the shoulder, you provide a bulbous bow, this is a vessel without a bulb, provide a bulbous bow, and obviously it is going to reduce the wave size and reduce the resistance of the ship. So the CFD analysis throw light onto these aspects. So what would be the gives information about the wave formation, or even to the flow pattern, the velocity around the fluid, the body, which increase the further frictional resistance and all that. So this helps in doing that. So this is actually meant for a naval project, which obviously this is still in the design stage, and so there is a scope for correction for the form. As I said before, inclusion of a bulb, properly designed bulb, is going to bring down the bow wave, and also a proper fine tuning of the form here in the shoulder also will reduce the wave size, and the resistance is expected to come down. You can see that the model also shows that it is a one without bulb, you can see that it is a rake stem, so there is no bulb here. So the provision of the bulb obviously will have a positive influence on the resistance of the vessel. So I think with that we conclude this lecture, and we will continue in the next class.